there, YouTube, and welcome to this next episode of the deferred rendering. So in this part of the tutorial series, I'll actually show how to start using this deferred pipeline, since now we have our basic building blocks of actually rendering. So I'll start out by simply we have update draw, we have update buffers, and then we have draw frame here. And we will start out by doing some stuff here. Let's see. This is move or set our swap chain back buffer as our render target. In an render target state, that is. This is what this is doing. Then we have clear the swap chain and depth buffer. And bind it as output. And you might immediately see that we don't want to do that. Right now, we update our buffers, we do some simulation of the lights. That's all fine and dandy, but when we want to draw a frame with this deferred pipeline, we don't want to render to the swap chain. We want to render to our render targets that we created up here. Let me close this so I don't have to scroll all over it. Shadow transforms, blah, blah, blah. Let's see. Let's do depth buffering here. Let's do viewport and scissor rect. Yeah, and then the camera matrix stuff. Okay, let's just rearrange this. So up here, I actually created these resources. I made sure that with this resource barrier here, whenever we're done creating the resources, that we register a transition into a render target. So that means that our resources here are actually ready to draw. Okay, so let's set our viewport and scissor rect, since we will render to the whole screen. And let's do a command call here where we set descriptor heaps, number of descriptor heaps, and let's do descriptor heap. And let's see, can I do a reference like this? And can we still run, or edit? Yeah. The API cannot be called on a close command list. Yeah, of course. Well, Let's see, we have some error somewhere. Yeah, we need to create an array here. Let's see. Descriptor heaps. Oh. Let's see, and git. Let's see. I always mess around with this binding here. Yeah, it removes the device. Oh, it's not a shader visible resource. So that's actually a bug. Let's see. So inside our descriptor heap here, this should be shader visible. Otherwise, the pipeline can't use it as resources. The others don't need to be shader visible as far as I remember. Since they are not known in the actual shader code. The render target, for instance, is not known inside the shader code. It can only be referenced. Okay, so as you see, this is now possible to bind to our descriptor as our descriptor heap. We want to start setting up our pipeline. And we want some of the same information here. So let's use that. And let's comment it so that we can show that we actually moved it. Okay. Let's take our deferred pipeline. Oh, whoops. Pipeline here and bind it. And let's set our constant buffer stuff. I mean, this is going to be within the draw call. So this is the preparation for the whole draw stage. Then we want to set our render targets, and we also want to clear them. So let's do something like, what did we set as our clear color actually? Clear value, color. Let's do 0, 0, 0, 0 here. Too many initializer values. Oh, okay. There we go for, no? Baby, please. Let's see. All right. Let's see. Uh, maybe just 0? No. I can't set the clear color or what? Oh. And this is also a union, it seems, so I can't set both the depth stencil and maybe even 0 on the alpha. Yeah, I think yeah, the alpha needs to change as well because remember we're storing different stuff in the W component or the alpha component. So let's actually set the clear color like that. Okay. So let's copy some of this code here. So our clear color is supposed to be like this, but our handles here will be our, and this is the CPU descriptor handle. So we will access our deferred renderer output textures descriptor heap here and build a series of descriptors on it. So get CPU handled 0, and then of course 1, and then the last one. So we set our RTV handles, and we need to bind our render target, or rather clear our colors here for all 3. We do have a stencil. I don't. Oh, we're using it, aren't we? Yeah, we're using it for the current shadows. It's fine. Maybe not this stencil. I don't care about this stencil right now. In the pipeline state here, stencil depth. Yeah, stencil. Now this is using stenciling, right? Yeah, it's using stenciling. Okay. Let's just clear it. And then we need to set our render targets. Number of descriptors is equal to 3. And there we go. All right. So that simply is the setup we need. We set our viewports. We bind our newly created descriptor heap. And that's why I call it our universal descriptor heap, because although it's called deferred SRV descriptor heap right now, this is a fairly expensive operation, so you should preferably only do it once. And therefore, it should be able to hold descriptors for all pipelines. And we will expand it with a shadow buffer, a shadow map reference as well. So we bind the root signature, we bind the pipeline state for a deferred pipeline, we set the topology and bind our index and vertex buffers. Then we prepare some clear colors, and find our render target views and add them to an array. We take our depth stencil handle as well, and we clear our buffers so nothing remains inside them on our 4 components from last frame. And then we clear our depth and stencil view, and we bind our render targets to our current pipeline, meaning that right now we have 3 render targets bound. And then we can do some drawing. So we bind our pass data in order to draw. And if we were to draw an object, we would do like this. So let's move that into this and then comment this out. Also comment out all of this stuff here. So this is binding of the shadow pipeline. And then we transition out of the render target of the swap chain, which is fine. Basically, we want to move this down here to the bottom, because in between here, we will still want to clear our back buffer, and I'm not sure we want to clear our depth stencil here, but I don't think we want to set this. So yeah, because we won't use the depth stencil per se. Let's see, transition the swap chain back buffer into a present state. And then we have close command list and execute plus present. There we go. Okay, right now we should only see a black screen. Nothing should really work, but that is intentional. Let me move this code outside of here. Because we currently swap to a different pipeline, and right now our vertex and pixel shaders are like this. So we might see a white color on one of our render targets. Let's see, because this command here just renders white to the render target. Let's do insight here. And let's check it in our utility here. Didn't I capture a frame? Disconnect. Let's see. Maybe. Okay, there we go. So if we access our resources, our first one, it's white. Lo and behold. What are the other ones? It's also white. They're all white. So let's step through the calls here. So we set our viewport, our sysdirect, our descriptor heap, graphics pipeline, deferred pipeline, set our primitive topology, we clear our buffer, for some reason it doesn't seem responsive. Okay. Then we bind our render targets, and then we do some drawing. Okay, something's wrong here with Inside. I usually don't find much success using Inside, and RenderDoc is way more stable for some reason. Anyway, let's try running it in RenderDoc. Let's launch this, and let's see. Let's see resources, render target 1. Let's see. Okay. Is it because we don't? Let's see mesh viewer here. We have our mesh. So in our pipeline. Oh yeah, of course, we don't actually translate into clip space. We can't do this because there are no vertices on screen. So I was way too early in terms of actually testing this in RenderDoc. Also NVIDIA Inside for that matter. So let's create our structures here. For our vertex shader here in our deferred pipeline, we will pass out this. We will have some pass data as well, some object data, some stuff like that. Yeah, so our vertex shader should basically mirror our let's just copy it actually. Our vertex shader should be the exact same thing because we want our normal and our position to be translated. As far as I remember. But we also want a float position world space here that we call position 0. And let's do output position world space. Let's do float 4 here. We could also just do like okay. Yeah, so let's do some modification after all. Okay, so world position. No, not it. Input dot position. Okay, and this is supposed to be world position dot XYZ. And this is just going to be multiplied by our world position here. We could call this clip space here. So we have our world position, which is after we do our transformation by the object matrix, and then into clip space, and then we transform the rotate the normal, also from the what do you call it, object transform. Okay, let's whoops, that's not it. Let's see. Let's copy these shaders and overwrite them. Okay, and let's do, I think render doc is faster. Okay, we have a warning somewhere. Warning treated as error, implicit truncation of vector type. Oh, let's see. It's not this one, I think. It's in the deferred one, right? Yeah. So let's close this. Deferred, so position clip space. Which line? Oh! There we go. Okay, let's try that. And now let's see if we have a result. We have a result. So since our pixel shader is just rendering white, that's what we get. So our object gets rendered with a white color. So let's look into our decision here. Okay. We want to draw our position in world space into one of our buffers and our normals, and actually also a material index. But let's forget that for now, and our albedo color, which is related to our material. Okay, so our pixel shader here, instead of outputting just a float 4, it should output a struct pixel shader output. And let's do a float 4 position. And let's do a comment here. Whoops, a struct. Last component could be object index W here. Then we do a float for normal. Last component W could be material index. And then a float for here, albedo color. And we want to output this, and we don't want to output this. And we want some input as well. We want some, let's see, I don't think we actually need the light data, but I don't mind. We also need some input here. Let's do an input here. Okay. And let's do, of course, a semicolon here. Okay. So what we now want to do is actually bind these to our different textures. So if we do something like this, this will be our first render target. This will be our second render target. And this will be our fourth render target, or rather third. Okay. So let's start creating our output here. For now, our output here, position, will just be our input dot position in world space. But of course, with an extra component here for now. And let's do our normal. And then our albedo color here, which is something that we will compute. So in our previous pixel shader here, we have some material data, which is called our diffuse color, diffuse albedo. That's pretty good, huh? We don't need that. So we have some material data. We also have some past data, but I'm not sure we actually need to bind it. So right now we bind it for every kind of like object. So we can just do g material color or material data diffuse albedo. And then we simply return our output here. Okay, so that's our shader. Once again, let's build everything here, and nothing actually renders to screen because we're not done with that yet. But let me just copy these shaders and then actually test it in RenderDoc. So let's see. And let's see our resources here. And immediately see, this is the position. This is the normals. Which is pretty interesting. Huh. Anyway, and this is the diffuse albedo. So we have a solid color. Since our material is like that. Okay. Let's see. So our normals and our depth buffer is also rendered. So immediately you see we have 4 buffers whenever we draw. I'm unsure whether vertex shader out. Solid color. Flat shaded. Anyway. Yeah, there's no rotation of the normals itself. Okay. Let's try actually drawing something more. So let's draw the other object. So back in the day we did this one and then we did this one. So let's try drawing that as well. Okay. Let's compile that and check it in our render doc here. Let's see the positions here, the normals. Let's see. Yeah, so this is in world space coordinates. Anyway, so you might say, what's up with all of this? This is basically a way to do efficient shading, which many graphics engines do. The only problem with it is really that it doesn't handle transparent objects very well, but transparency in a Toon shader is something that is more of a gimmick, I think, anyway. So stylistically, it doesn't matter. Anyway, we're still not getting anything onto our screen, and that's because although we're kind of like rendering to our geometry buffer or whatever we call it, we're actually not rendering anything to our screen. So in order to do that, we want to process all the pixels for the objects. Yeah, so let's create a pipeline that does that. So in our deferred pipeline here, let's see, deferred pixel pipeline. And in our renderer API, we want to initialize a pipeline here, but the way that we actually, let's see, void initialize pixel process. And let's do a shader directory that's called post effects, since we will also be adding some stuff for that. So it will have a vertex shader, which we will not include in our project, and then we will do deferred lights, and we will create a pixel shader for that. And the reason why I'm doing it in different folders here is because we're gonna be able to specify a, let's see, this is, yeah, let's just do a stdw string here, pixel shader path, Let's do most of this stuff here, I think. So we will do post effects vertex shader and then the pixel shader path here, C string. Okay. Our blend state is fine. Our culling is fine. We don't do any depth testing. DXGAI format unknown. Okay. Our input elements is just, we will create a random triangle that is able to span our entire screen. So we will just pass in a position here. Let's see, we will only add one element. And we will do one render target. And yeah, I think that's it. So initialize pixel process here with our device.get. And then we want a shaders post effects. Let's see, deferred lights. Pixel shader.hlsl. And let's do this. Deferred pixel pipeline DSO. And let's see if we can compile and run. We can. So far. Okay. Great stuff. So inside our vertex shader here, let's open a previous one where we simply get a position here and we will return, let's see, a series of yeah, I have this in a different, what do you call it? I actually have this code from a different project, so I'll just port it over. So what this does is it takes three vertices and renders them to the entire screen and builds a set of UV coordinates for those pixels so that every pixel gets mapped precisely to where it should be. And it, of course, takes the vertex ID as a parameter in order to manipulate the UVs. You would know that they go from 0 to 1 on both the X and Y axis. We pass them out for each vertex. Imagine a triangle that's so big that it fills out the entire screen, and the parts of the triangle that's outside of the screen just gets culled by the rasterization stage. And we of course want the pixel location in clip space on our screen. We don't have a W parameter, or rather depth parameter, and we don't manipulate the W because we want to keep the perspective. So that's basically what this shader does. And then this should just render white. Okay. So that's part one. And let's see if we can actually use this pipeline to render something white to our screen. So we do all this stuff here. And down here, when we have set our pipeline state, or rather our graphics rendering stuff, back to our back buffer. In between here, where we transition the pipelines, or rather the render targets on the back buffer, or rather swap chain. We want to set the pipelines here. We still want the same vertex and index buffers. Maybe we even want this here, and then we clear the render targets, and then we do our draw call. And it basically doesn't matter how many vertices we draw, or rather what we draw. Let's just draw 3 random vertices. Since we're not using the position or the normal or anything from them, we'll just do like this. And we have a white screen. And just to let you know that this actually works, you can see that whenever we change the pixel shader, we actually change the color. Okay, great stuff. So now we actually have a pipeline that handles all of our pixels. So now we need to couple our deferred pipeline to our actual pipeline, which renders to our screen. Excuse me. And how do we do that? Well, the shader here needs some kind of like, well, I need some resources. How about the position of the object on the pixel? I need that. How about the normal of the object on the pixel? I need that. How about the diffuse color? I need that. Luckily, that's what we actually rendered to our geometry buffers. So somehow we need to get it into the shaders. And how you do that in DirectX 12 is to set up your so-called root signature in order to allow for access into these, what do you call it? Kind of like textures, or yeah, just these resources, I guess. So first we need a root parameter here. And we want a so-called descriptor table, because we will have a series of textures, and we need a range for that. So let's see, can we find it? Descriptor range. Okay, so we need that as well. So first let's increase the size of this so we don't get into trouble, and then create a range array here, and let's set range 0, range type. We will use SRVs. Remember that during our creation of our textures here, we actually created, not here. Oh, I collapsed it, did I? Yeah. So up here, I actually created the SRVs for the same resources that we use as our geometry buffer output, or geometry pass output. Let's see. Register space will be 0. And the base shader register will be 0. And let's see, the number of descriptors will be 3 because, well, we created 3 textures. And the offset, let's see, I can't remember the append thingy, the append macro. Let's see, can I find it somewhere? Yeah, there we go. And we of course need some flags as well. Am I not allowed to? Flags? No. Well, I guess not on this type here. Let's see, am I using the wrong struct? Oh yeah. It's because we're using the basic root signature, not the 1.1. Okay. And if that didn't make any sense to you, don't worry. It's more advanced stuff. Pointer to the range here. One. And let's see. Parameter type. Let's do a descriptor table here. Let's just do this shader visibility. All. And let's increase this to 4. We have no samplers right now. We will also need samplers in order to actually sample our resources. But first, let's see. Let's see. Num descriptors cannot be 0. All right. Let's do this. Does that help? No. Let's see. Oh, whoops. Haha, whoops. Num descriptors here. Okay. Okay, we're back to our purple or teal screen. Okay, so now in our root signature, we have actually created space in order to bind our resources. So what you can do is simply, like whenever we bind resources, we do something like this. So before we do this draw command here, we could do set our table, set graphics root descriptor table, which is our parameter index number 4, and we grab our deferred rendering SRV descriptor heap here, but here we need this GPU handle, and we will simply give it our handle of our first descriptor, and it should fill out the whole table with the following descriptors. Great stuff. All right, so that means that we can actually do something like a texture 2D here. G position buffer. Let's see, register T for texture, or rather, yeah, it's not really texture, I guess, but it's the T letter. Normal buffer. And let's do albedo buffer. And let's see in RenderDoc, let me just copy these shaders. Let's see. Whenever we set this, let's see, high blind state. But at least we bind the descriptors here. Of course, we don't sample them. So we should probably create a static sampler here. Let's create 2. Let's see. Static samplers. These are samplers that can be accessed all throughout the shaders. That's the D3D12 static sampler description here. Sampler disks. Let's just create 2 here. And let's fill out the first one. And this is the UV. And let's do clamp, because we don't want to sample outside our texture. And let's do VW as well. Let's do a filter here. And let's do min-max MIP point comparison. Let me see, what do I actually use for point sampling normally? Let's see, D3D12 filter minimum magnification MIP point here. And this is the, and let's do shader register. The first one is this one. And then the register space. Okay. Then we want the minimum level of detail to be 0. Max level of detail to be RD3D12 float 32 max. MIP LOD bias. Let's not add any of that. And let's do max anisotropic filtering 1. let's just do a comparison function. It will always pass. And let's do shader visibility here. All. And let's copy this. And of course, set it to shader register 1 here instead. And instead of this, let's do linear so that we can use that kind of sampler. Number of static samplers, and let's do static sampler description here. Let's see if I can compile this. Yeah, I can compile it. Okay. Sampler state g point sampler point clamp sample. Let's do sampler register sampler space 1. Let's do linear. Okay, and let's do some color sampling here. So let's just try color. Let's sample our G position buffer here. Sampler with our S point clamp with our, okay, we don't have our input here. So we need that from this vertex shader output here. Vertex shader output, let's see, vertex shader output input. So let's grab our UV, yeah. Let's set the color alpha to 1, and let's just return our color. Let's see, do we get any errors? No, we simply render our, what do you call it, position to our screen now. Okay. So we could change this to our normal buffer instead. And we would get the normal color or the albedo. And we would get the solid color. So now we can actually do our lighting computation. So in our base pixel shader here, we do something like this. And we can simply steal some of it. Okay, we also need some pass data, I see. So let's make sure that it's bound as well. Okay, so let's see, let's bind our pass data. Okay. And let's see. Let's do some computations then. And remember the position and the normal and the albedo. We could do this in a step function, but let's just implement it as is for now. Let's do 1 or 0. 1, I guess. And let's do, okay. So we have our intensity stuff here. First, we want a flow 3 normal gnormal buffer dot sample s point clamp input UVs or XYZ. Okay, let's do float for albedo g albedo buffer sample s point clamp input UVs. There we go. Okay. We can now calculate our intensity by dotting our normal here with our light direction. Then we can implement this. And we can multiply by the albedo. Right now we're not using the position, but we might for more complicated lighting. There we go. So we immediately see that our lighting algorithm is back in action. And it's blazingly fast. I suspect at least. Because right now we're only doing one geometry pass. Or rather, we're not rendering the pixels and doing overdraw. Okay, let's draw the floor to our geometry buffer. And let's do floor. First one, or rather second one, first one here. And I'll of course, as we go along, create a more robust method for drawing our meshes. Maybe we want to automatically load the whole Blender scene. And yeah. Let's fiddle around with it anyway. So our Toon shader is back up and running, but the difference is that we're actually not spending a lot of time doing geometry, and we actually have some more information that we can use for our outline rendering. Okay. So we actually have deferred rendering, even though it doesn't seem like it made any difference. But we have the geometry buffer pass, as it's called, which is this, where the pixel shade outputs data, not pixels, for each object. Not even for the entire screen, but only wherever it has an object. Then we have our post effects, kind of like pixel processor, which gets run once we have knowledge of all of our geometry. Yeah. So that's basically deferred shading. And of course, it's way more powerful than the performance optimization, because now at our pixel shader stage, we have access to a lot of different information. And of course, I could also do, as I suggested in the pipeline state here, I could store different information in the different parts of whatever the texture content is, and I could also expand it with another buffer where I would maybe render even more data, like a movement vector, as it's called. So things in motion have a movement vector, and you can use that to kind of like do anti-aliasing and stuff like that. Yeah, so it's really powerful. Also, if we did multi-sampling now, on in terms of trying to stop aliasing, we would only do it in the actual shader here. Also, if we had a lot of lights, remember, it doesn't really matter that we got a lot of lights, because we only do this pass once for each pixel, not once for each pixel for a lot of different objects. Yeah. So now we can implement maybe 1000 lights and we won't have any lag. Yeah, but I know it doesn't seem like much. Maybe it's just me that feels that way, but it's actually done so far. And the next step is the actual shadow mapping. Yeah, but yeah, we should do that in a separate episode, and it will use a lot of the different stuff that we actually did here, like creating a separate pipeline, allowing resources both to be in one state and another. Yeah. If you're doing root signature 1.1, be mindful that you need to transition your resource states in between bindings on the different pipelines. But yeah, if you're using that, probably you know what you're doing. So yeah, but this is it for this part of the tutorial series. If you found it helpful, entertaining, inspirational, or something of the like, please consider commenting, liking, or subscribing. There's also a link to the GitHub repo and the Discord server in the description, and ways to support the channel. All right, please take care, and hopefully I'll see you in the next one. Bye bye.